Okay, so I'm going to attempt to record the first lesson without anybody in here. I'm not going to lie, it's a little weird talking to myself, but we'll see how it goes. Okay, so we are starting chapter 8, linear functions, the famous chapter 8. This chapter is a bit challenging just because it's a lot of new material. We're going to split it up and do the best we can to take it one step at a time. So one of the biggest questions that I get on this chapter is why, and when are we going to use this? So I'm going to give a little example, and then we'll come across more examples as we go through the chapter. But how can you use math to describe the steepness of a bike trail? So there is a trail, it's called Slick Rock Trail, and it's one of the most famous mountain bike trails in the world. An estimated 100,000, that's like the population of Tyler, people visit the trail each year. It may have been named by early settlers whose horses struggled to walk on the slick sandstone rock formations. So mountain bikers, however, find that their bike tires grip the sandstone extremely well. This traction allows bikers to ride up slopes that would otherwise be too steep for bicycling. Because the trail is only 12 miles long, which apparently isn't very long for a bike trail, there have been some problems with riders failing to take an adequate supply of water with them because they don't take into consideration how steep it is. And they underestimate how much hotter the sun can feel as they climb the trail. So for safety reasons, riders are urged to take twice as much water as they think they will need. And in the midsummer, when it's the hottest, they're encouraged to start the trail before 7 and be off before noon. So the steepness of a bike trail, such as the Slick Rock Trail in Utah, can be described by the ratio, which is a word we've heard all year, of the change in elevation from the horizontal distance traveled to the vertical distance traveled. So that's kind of where we're going with this, is we're going to be looking at ratios and change and how input is related to output and how to graph things. We're going to talk a lot about architecture and the different lines that go into building different structures. So some of the important vocabulary words for today are relation. Okay, so what is a relation? A relation is a set of ordered pairs. A set of ordered pairs. Now keep in mind that an ordered pair is like 2, -1. So that's one ordered pair. So a relation is a set, meaning more than one. Now a domain, the domain is the domain of a relation is the set of all inputs. And that is also known domain just asks us to list all of the hex coordinates, which are right here in the top boxes. So the domain would be 5, 10, 15, 20, and 25. The range is the output, which is all of the y coordinates, which are the bottom numbers. So the outputs would be 13, 12, That doesn't make sense. Now, when we're talking about example 2, the relation is not a function because the input 1 is paired with 2 outputs. So one time you put in the number 1 and you get out 1. The next time you put in the number 1 and you get out 3. That would be like back in the tree example. You measure the tree when it's a year old and you say that it's a foot tall, and then you come back later that day, the tree's still a year old, and you say that it's 3 feet tall. That doesn't happen. So therefore it's not a function. Okay, we're going to go to the last page of the notes. We're going to do 2 practice problems. And it just says, identify the domain and range of the relation to tell whether the relation is a function. Now, because I don't have a graph up here, I'm not going to represent this on a graph. I'm going to use a mapping diagram. So a mapping diagram looks like this. I put my inputs here, and I put my outputs here. And all I do on my inputs is I go through and I list from least to greatest the x coordinates. So by looking, here's an x, 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 x. So, and these happen to be in order from least to greatest. So the first input is -5. The next one is -3, then -1, then 2, then 5. So they gave them to me, the inputs were already in order from least to greatest. Now when you look at the outputs, they are not in order from least to greatest. So the outputs are all the y's. So which of these numbers, 2, -1, 0, 3, and 4, is the smallest? It would be -1, so I put that first. And then after -1, it would be 0. And then after 0, it would be 2. And then the last one would be 4. Did I get all of them? 2, -1, 0, 3, 4. 2. Oh, I forgot 3. There's 3. So I'm going to squeeze 3 in right here. Now, the next thing to do is to match using arrows, and I'll use a different color here. Match using arrows the input to the output. So go back up here. When I put in -5, or when my x coordinate was -5, what was my output? It was 2. So I'm going to draw a line from -5 to 2. And then I'm done with that one. And then I look at this one. When my input was -3, my output was -1. So I'm going to draw a line from -3 to 1. And I'm done with this one. Now here, when my input was -1, my output was 0. So I'm going to go from -1 to 0. Now when my input was 2, my output was 3. So I'm going to draw a line here. And then last, when my input was 5, my output was 4. So is this a function? Do I have the same input twice? No, these are all different numbers with different outputs. No. So I have all unique inputs and they don't have conflicting outputs. So therefore it is a function. Okay, now I'm going to go to this one and I'm going to do the same thing. I'm going to do a mapping diagram. Inputs. And remember, inputs are the domain. And then outputs, which are the range. I'm just going to do this right here. Now, I've got to put it in numerical order. So I've got my inputs, my x's are -4, -3, 0, 1, 2, 3, 3. So, again, they are already in order from least to greatest. So I'm going to go -4, -3, 0, 1, 2, 3, and I'm only going to do 3 once, even though it's listed twice. Now I'm going to go back and list my outputs, which are my y's. And again, I've got to do this in numerical order. So from least to greatest, the smallest up here would be, the smallest output would be -3. And then it would be -2. And then it would be -1. And then it would be 0. And then it would be 1. check and make sure that you did it right. How many outputs do we have? 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. So I got all. Now, the next thing to do is draw arrows. So when my input is -4, my output is -3. Done with that one. When my input is -3, my output is 2. So I go there. Done with that. When my input is 0, my output is 0. Done with that one. When my input is 1, my output is -1. Done with that one. When my input is 2, my output is 3. Done with that one. And when my input is 3, my output is 1. Done with that one. And then when my input is 3, my output is -2. Done with that one. So is this the function? No, not a function. Why? Because one time you put in 3 and you get out -2. And the next time you put in 3, you get out 1. So it doesn't make sense if you're thinking about a machine here. If you put in something and you get out something one time and you put the same something in the next time and you get out something different. Doesn't make sense. Not a function. Okay, so last example, it says in the graph below, no vertical line passes through more than one point. So the relation represented by the graph would be a function. So it is a function. And I'll show you how you do this. Okay, so draw a vertical line here that goes through this point. Is there only one point on this line? Yes, so we're good there. Now draw a vertical line here. Is there only one point here? Yes. There's no points on this line, so don't worry about that. Now draw a vertical line here. Is there only one point on it? Yes. Draw a vertical line here. Is there only one point on it? Yes. Draw a vertical line here. have to put them in order and draw the arrows. So on 3, 4, 5, and 6, again, you don't have to do the mapping diagram, you just have to do what I'm doing. So the range, or the outputs here, would be 2, 4, 6, 8, 10. That's it. 2, 4, 6, 8, 10. Those are all the Y's. So that's all you're doing for 3, 4, and 5. Number 7, 8, 9, and 10, it does tell you to do the mapping diagram. And not only do you have to do the mapping diagram, you have to identify whether or not it is a function. It says explain your reasoning. The mapping diagram is enough to explain your reasoning. Okay, so I'll do this one over here. I'll do number 7. So we've got negative 2, 1, 0, 4, 1, 3, and 2, 3. So the mapping diagram is going to be my inputs and my outputs. My inputs are going to be in order from least to greatest, negative 2, 0, 1, and 2. And that was just my x's. Negative 2, 0, 1, and 2. Now my outputs are going to be here. 1, 4, 3, and 3. So I'm going to do in numerical order from least to greatest. 1, 3, and I can go ahead and draw 3 twice on the output. 1, 3, 3, and 4. Now all I've got to do is draw my arrows. When my input is negative 2, my output is 1. When my input is 0, my output is 4. When my input is 1, my output is 3. And when my input is 2, my output is 3. Which is fine. Even though I have a double number here in the outputs, you can have a double number in the outputs. You can't have a double number in the inputs with 2 different outputs. So this is still a function. So you'll do that on numbers 7 through 14. Number 15, 16, and 17, that's just the vertical line test. And all you got to do is draw your lines there. And then number 18 and 19 are just thinking problems. I want you to try those. So it shouldn't take you too long. So we will grade this homework when I get back on Monday. You may need to reference your book or download the study guide, which is available. And then obviously this video is going to be available